Hello students, welcome to this lecture on three-dimensional geometry. In this lecture, we will cover NCERT section 11.1, 11.2, example 1 to 5, exercise 11.1. This is disclaimer. First, we will start by looking at introduction on three-dimensional geometry. Then we will look at direction cosines and directions ratios of a line. Next, we will focus on direction cosines of a line passing through 2 points. Next, we will solve NCERT examples 1, 2, 3, 4, and 5. Finally, we will solve NCERT exercise 11.1, right? So, I hope you are with your notebooks and pens ready. So, let's start. So, we will now start by understanding what three-dimensional geometry is. So, in 3D geometry, we study shapes and objects in space using three coordinates x, y, and z. Every point in space can be described by these three numbers. Okay, so using three coordinates x, y, z, we define 3D geometry. So in this chapter, we will study the direction cosines and direction ratios of a line joining 2 points. For example, if a line passes through points A, x1, y1, z1 and B, x2, y2, z2, okay, then the direction ratios are x2 minus x1, y2 minus y1 and z2 minus z1. Next, we will discuss about the equations of lines and planes in space. The angle between two lines, two planes, a line and a plane, sort as distance between two skew lines and distance of a point from a plane. So let's talk about some real world applications of three-dimensional geometry. First, consider architecture and constructions. Engineers and architects use 3D geometry to design buildings, bridges, and other structures. Next, let's look at navigation and mapping. GPS system and mapping applications rely on 3D geometry to determine locations on Earth. Okay, so for instance, your phone uses coordinates, latitude, longitude, altitude to pinpoint your position and help you navigate from one place to another. Then, in science and research, so 3D geometry is essential in science and research. So astronomers use it to calculate the positions and movements of celestial bodies, and physicists use it model complex phenomena like the motion of particles in space. Okay, so now let's start by talking about direction cosines. So direction cosines are three numbers that help us describe exactly how a line is pointing in three-dimensional space. So they give us a unique way to define the direction of the line in three-dimensional geometry, which is really important for understanding geometry in higher dimensions. So now imagine we have a line which we will call L that passes through the origin, and this line makes three different angles with the positive x-axis, y-axis and z-axis. So we call these angles alpha, beta and gamma. Then the cosines of these angles cos alpha, cos beta and cos gamma are called the direction cosines of the line L. They are usually denoted by L, M and N. That is, L equals cos alpha, M equals cos beta and N equals cos gamma, right? Now, when a line's direction is reversed, then what happens when we reverse the direction of a line in three-dimensional space? So when we do this, the direction angles of the line become their supplements. Okay, so that means if the original angles are alpha, beta and gamma, then the new angles are pi minus alpha, pi minus beta and pi minus gamma. Thus, the signs of the direction cosines are reversed. So now let's consider that every line in space can be extended in both directions. This means that each line actually has two sets of direction cosines, one for each direction. Okay, so for example, if one direction has a direction cosines L, M and N, the opposite direction will have minus L, minus M, minus N. Okay, so this duality is a key feature of lines in three-dimensional geometry. To avoid confusion and to have a unique set of direction cosines for a line, we need to treat the line as a directed line. Okay, so that means we specify which direction along the line we are considering. Okay, by doing this, we can assign a single unique set of direction cosines to the line, so rather than having two possible sets. Once we have chosen a direction for the line or made it a directed line, the angles alpha, beta and gamma are uniquely defined with respect to the positive coordinate axis, and consequently the direction cosines L, M, N becomes unique. But what if the line doesn't pass through the origin? In that case, we can still find its direction cosines by drawing a parallel line that does pass through the origin. Okay, so this approach allows us to use the same methods for finding direction cosines, no matter where the line is located in space. So now to find direction cosines when line doesn't pass through origin, okay, the first step is to draw a line through the origin that is parallel to the given line. Next, we find the direction cosines of this parallel line through the origin. Since the direction of the line has not changed, the direction cosines we calculate here will be the same as those for the original line. Finally, it's important to note that both the original line and the parallel line through the origin will have the same direction cosine. Okay, so this method ensures we can always determine the direction cosines for any line in space, even if it doesn't pass through the origin. Now, we will explore in more details direction cosines and coordinates. So let us consider the origin, which we will call point O, and another point P with coordinates x, y, z that lies on a line L. The distance from O to P is r, so we can write this modulus value of OP is r. Okay, then let's look at the x coordinate of point P. So we can express it as x equals r cos alpha, which is also written as x equals L times r. Here, alpha is the angle between the line OP and the x-axis, and L is the direction cosine along the x-axis. Okay, so this equation shows how the x coordinate depends on both the length r and the direction of the line. Next, for the y coordinate, we have y equal to r cos beta, or it can be also written as y equals m times r. So beta is the angle between the line OP and the y-axis, and m is the direction cosine along the y-axis. Okay, so this formula tells us how far along the y-axis the point P is, and based on the direction and length of OP. Similarly, for the z coordinate, we use z equals r cos gamma equals n times r, where L, m and n are the direction cosines of the line L. Now, let's explain why these formulas work. So to find the x coordinate of P, we project the line segment OP onto the x-axis. So this means we are looking at how much of OP points in the x direction. And the formula x equal to r times L comes from this projection, where L is the cosine of the angle with the x-axis. To find the y coordinate of P, we project the line segment OP onto the y-axis. Okay, and the formula y equals r times m tells us how much of OP points in the y direction, with m being the cosine of the angle with the y-axis. To find the z coordinate of P, we project the line segment OP onto the z-axis. To do so, we are going to use trigonometry here. First, imagine a right angle triangle formed by 3 points: O, which is the origin, P, which is a point in space, and the projection of P on the x-axis. So this triangle helps us visualize how the position of P relates to the axis. Okay, so think of a right angle triangle formed by O, P, and the projection of P onto the x-axis. So look at this diagram. Notice how the triangle is laid out. So O is at the origin, P is somewhere in space, and the projection of P onto the x-axis. Okay, here this point here, and this forms, these 3 points forms the triangle. Now In this triangle, the hypotenuse is the distance from O to P, which we call R. So R equals the length of the vector OP. The angle between OP and the positive x-axis is called alpha. So this angle tells us how much the line OP is tilted away from the x-axis. Now, using basic trigonometry, we know that the cosine of alpha is equal to the base divided by hypotenuse. So in this case, cos alpha equals x divided by r, where x is the x coordinate of the point P and r is the length of OP. If we let L represent cos alpha, and remember that r is the length of OP, so we can substitute these into our equation to get x equals r times L. Now, let's focus specifically on the y coordinate. So we are going to see how the y coordinate of a point in space can be found using direction cosines. So pay attention to how we use the angle with the y axis in this process. So think about a right angle triangle formed by the origin O, the point P, and the projection of P onto the y axis. So let's start by looking at the direction cosines, okay, and how they relate to the coordinates of a point in three-dimensional geometry. So look at this diagram, okay. So in this diagram, here the vertices of this triangle are basically O, P, and the projection of point P onto the y-axis. In this triangle, the hypotenuse is the distance of the origin to the point P, which we call R. So distance between OP is R. Okay, remember R represents the length of the position vector from the origin to the point P. Then the angle between the line OP and the positive y-axis is called the beta. Okay, so this angle is important because the direction cosine with respect to the y-axis is defined using the angle beta. So using now basic trigonometry, we know that the cosine of beta is equal to the base divided by the hypotenuse. So in this case, cos of beta equals y divided by r, where y is the length of the projection of OP onto the y-axis and r is the length of OP. Now let's substitute what we know. Okay, so the length OP is r and the direction cosine with respect to the y-axis is m. So cos beta equals m. Now plugging these into our equation, so we get y equals r times m. So this is our equation, y equals r times m. Now for the z coordinate, imagine a right angled triangle formed by 3 points: O, which is the origin, P, which is our point in space, and the projection of P onto the z-axis. So now look at this diagram. Okay, in this triangle, the hypotenuse is the length from O to P, which we call R. So distance between O and P equals R. This is the straight line. distance from the origin to our point in space. The angle between OP and the positive z-axis is called gamma. So this angle tells us how much OP is tilted away from the z-axis, and we will use this angle to relate the z coordinate to the length r. So using now basic trigonometry, we know that the cosine of gamma is equal to the base divided by hypotenuse. So in this case, cos gamma equals z divided by r, where z is the length along the z-axis and r is the length of OP. Now, if we substitute length of OP equals r and cos gamma equals n into the above relation, then we will obtain z equals r times n. Now, we are going to explore an important concept in three-dimensional geometry, the relationship between the direction cosines of a line. Let's start with the theorem. So in this theorem states that for any line, if we call its direction cosines L, M and N, then the sum of their squares is always equal to 1. Okay, in other words, L square plus M square plus N square equals 1. So this is a fundamental property that holds for any line in three-dimensional space. Now, let's prove this theorem step by step. So, let's consider a point Px, y, z on a line with the direction cosines L, M and N. Next, let's define R as the distance from the origin O to the point P. So, R is just the length of the line segment OP. Now, using the distance formula, we have OP square equals x square plus y square plus z square, and this is equal to r square. Okay, this equation simply comes from the Pythagoras theorem extended to three-dimensional. Now let's recall how direction cosines relate to the coordinates of P. So by definition, we have x equals L times r, y equals m times r, and z equals n times r. So this means each coordinate is the product of the corresponding direction cosine and the distance r. Let's substitute these expressions for x, y and z into our distance formula. So we get L times r whole squared plus m times r whole squared plus n times r whole squared equals to r squared. Now let's factor out r square of each term on the left side. Then we have r square times L square plus m square plus n square equals to r square. Finally, we divide both sides of the equation by r square, which gives us L square plus m square plus n square equals 1. So this completes our proof and confirms that the sum of the squares of the direction cosines of any line is always 1. Now, let's discuss direction ratios. Okay, so any three numbers which are proportional to the direction cosines of a line are called the direction ratios of the line. So now let's look at the relationship between direction cosines and direction ratios. Suppose L, M and N are the direction cosines and the A, B, C are the direction ratios of the line of a line, then A equals lambda times L. Then B is related to the direction cosines M in the same way. B equals to lambda times M. The direction ratio C is given by C equals to lambda times N. For some non-zero scalar, lambda belongs in set of real numbers. So this can be rewritten as L divided by A equals M divided by B equals N divided by C. So this is the relationship between direction cosines and direction ratios of a line. Now, let's start by addressing a common misconception in three-dimensional geometry. So, notice here that direction ratios are not unique. Okay, this means that there can be many different sets of numbers that represent the same direction of a line. Okay. So let's look at this more closely. So if A, B, C are direction ratios of a line, then K times A, K times B, and K times C for any K not equal to 0 are also direction ratios of the same line. However, direction cosines, which we usually write as LMN, are unique for a given directed line. Now we will start by finding direction cosines from direction ratios. So let's start by expressing the direction cosines in terms of the direction ratios. So we use the variables L, M, N for the direction cosines and A, B, C for the direction ratios. So we can write L equals A times K, M equals B times K, and N equals C times K for some constant K. Now remember the key identity of direction cosines. The sum of their squares is always 1. That is L square plus M square plus N square equals 1. Next, let's substitute the expression for L, M, and N into the equation. So we get AK whole squared plus B times K whole squared plus C times K whole squared equals 1. Now solve for K. So K square times A square plus B square plus C square equals 1. So it implies K equals plus minus 1 divided by square root of A square plus B square plus C square. Now let's substitute the value of K back into our expression for L, M, and N. So remember, L, M, N are the direction cosines, and we have L equals A times K, M equals B times K, and N equals C times K. So we are now substituting back K into L equal to AK, M equal to BK, N equal to CK to find L, M, N. So we are getting here L equals plus minus A divided by square root of A square plus B square plus C square. M equals plus minus B divided by square root of A square plus B square plus C square. N equals plus minus C divided by square root of A square plus B square plus C square. So note these formula. Okay. So these formulas will help us to find direction cosines if we have given direction ratios. Now we will look at the direction cosines of a line passing through 2 points. So first remember that through any two given points there is exactly one straight line that can be drawn. Okay, this is a fundamental property in geometry and it's important because it means the direction of the line is uniquely determined by those 2 points. Okay, so now let's see how we can actually find the direction cosines for a line passing through 2 points. Suppose the 2 points are P with coordinates x1, y1, z1 and Q with coordinates x2, y2, z. So the direction ratios of the line are given by x2 minus x1, y2 minus y1 and z2 minus z1. Okay, let's see here. Now draw perpendicular from P and Q to xy plane to meet at R and S. Okay, so here visualize the diagram. Now draw a perpendicular from P to QS to meet at N. Let L, M and N be the direction cosines of the line PQ and let it makes angles alpha, beta and gamma with the x, y and z axis respectively. Now let's look at the geometry. In the right angle triangle PNQ, the angle PQN is gamma, which is the angle between the line and the z-axis. So look at this diagram. Therefore, from the triangle PQN, cos gamma equals base divided by hypotenuse equals to NQ divided by PQ, and here NQ is basically Z2 minus Z1. So cos gamma equals to Z2 minus Z1 divided by PQ. Similarly, cos alpha equals x2 minus x1 divided by PQ and cos gamma equals y2 minus y1 divided by PQ. Since cos alpha equals x2 minus x1 divided by PQ, cos gamma equals z2 minus z1 divided by PQ and cos beta equals to y2 minus y1 divided by PQ. So now direction cosines of the line segment joining the points P x1, y1, z1 and Q x2, y2, z2 are x2 minus x1 divided by PQ, y2 minus y1 divided by PQ and z2 minus z1 divided by PQ. Where PQ is the distance between the 2 points calculated as the square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Suppose we have 2 points P with coordinates x1, y1, z1 and Q with coordinates x2, y2, z2. Then the direction ratios of the line segment joining P x1, y1, z1 and Q x2, y2, z2 may be taken as x2 minus x1, y2 minus y1, z2 minus z1. So the direction ratios of the line segment joining P and Q are x2 minus x1, y2 minus y1 and z2 minus z1 or x1 minus x2, y1 minus y2 and z1 minus z2. Now let's look at example 1. So in this example, we have given if a line makes angle 90 degree, 60 degree and 30 degree with the positive direction of x, y and z axis respectively, then find the direction cosines. So first of all, try it yourself, then see solution. So let's solve this question step by step. First, let's restate the information given. The line forms an angle of 90 degrees with the x-axis, 60 degree with the y-axis and 30 degrees with the z-axis. So it's important to keep these angles in mind as we move forward. So the direction cosines are usually represented by the letters L, M and N. Here L is the cosine of the angle with the x-axis, M is the cosine of the angle with the y-axis and N is the cosine of the angle with the z-axis. To find the direction cosines, we simply take the cosine of each angle that the line makes with the coordinate axis. So we will calculate here cos 90 degrees, cos 60 degrees and cos 30 degrees. Thus, L equals cos 90 degree equals 0, M equals cos 60 degree equals 1 by 2, N equals cos 30 degree equals root 3 divided by 2. So let's check if these values are correct by verifying the fundamental relation for direction cosines. L square plus M square plus N square equals 1. So substituting our values, we get here the direction cosines of the line are 0, 1 by 2, root 3 by 2. Okay. Now let's look at another example, example number 2. So in this example, the question asks us to determine its direction cosines. And here we have given a line which has direction ratios 2, -1 and -2. So first of all, try it yourself and then see solution. Let's solve this example step by step. So first, let's recall the relationship between direction ratios and direction cosines. If a line has direction ratios A, B, C and then their direction cosines L, M, N are given by L equals plus minus A divided by square root of A square plus B square plus C square. M equals plus minus B divided by square root of A square plus B square plus C square. N equals plus minus of C divided by square root of A square plus B square plus C square. Given here, A equals to B equals -1 and C equals -2. Now we will substitute these values into the formulas for L, M and N. That means we will calculate L equals so let's find the direction cosines L, which is the cosine of the angle with the x-axis. So the formula for the direction cosine is L equals plus minus 2 divided by square root of 2 square plus -1 square plus -2 whole square. And after simplifying, this is equal to plus minus 2 upon 3. Next, let's calculate the direction cosine M, which is the cosine of the angle with the y-axis. So the formula is M equals plus minus -1 divided by square root of 2 square plus minus 1 whole square plus minus 2 whole square. This is equal to plus minus 1 by 3. Then after substituting the values, we get the n equals to plus minus 2 divided by square root of 2 square plus minus 1 whole square plus minus 2 whole square equal to plus minus 2 by 3. Now let's look at example 3. In this example, we have to find the direction cosines of the line passing through the 2 points minus 2, 4, minus 5 and 1, 2, 3. So first of all, try it yourself and then see solution. So let's solve this example step by step. To start, let's recall the general formula for the direction cosines of a line passing through 2 points. So if we have points P with coordinates x1, y1, z1 and Q with x2, y2, z2, then L equals x2 minus x1 divided by PQ, M equals y2 minus y1 divided by PQ, N equals z2 minus z1 divided by PQ, where PQ is square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Given here, P is minus 2, 4, minus 5 and Q is 1, 2, 3. So we will use these values for x1, y1, z1 and x2, y2 and z2 in our calculation. So PQ equals square root of 1 minus 2 whole square plus 2 minus 4 whole square plus 3 minus 5 whole square. It implies PQ equals square root of 3 whole square plus minus 2 whole square plus 8 whole square equals to square root of 77. Now that we have PQ, so let's write the direction cosines for the line joining these 2 points. So the direction cosines of the line joining 2 points are L equals 3 divided by square root of 77, M equals minus 2 divided by square root of 77 and N equals 8 divided by square root of 77. Now let's look at example 4. In this example, we have to find the direction cosines of x, y and z axis. So let's see the solution of this example step by step. The direction cosines of the x-axis, we consider the angle between the x-axis and itself, which we call alpha. Okay, and since the x-axis is parallel to itself, the angle alpha is basically 0 degrees. So this is always true for any axis with itself. So cos alpha equals cos 0 degree equals to 1. Next, let's look at the angle between the x-axis and the y-axis, which we call beta. Okay, so the x-axis and y-axis are perpendicular to each other. So the angle beta is 90 degrees. So now calculate cosine of this angle. So we have cos beta equals cos 90 degrees, which is 0. Now let's consider the angle between the x-axis and the z-axis, so which we call gamma. Again, these axes are perpendicular, so gamma is also 90 degrees. So the cosine of gamma is cos 90 degrees equals to 0. This means the x-axis has no component in the z direction either. Therefore, the direction cosines of the x-axis are 1, 0, 0. I hope this example is clear to all of you. Now, we will find direction cosines of the y-axis. First, let's consider the angle between the y-axis and the x-axis. The y-axis is perpendicular to the x-axis, so the angle alpha is 90 degrees. This means cosine of alpha is cos 90 degrees. So cosine of alpha equals cos 90 degrees equals to 0. Next, let's look at the angle between the y-axis and itself. So which is the y-axis itself, since the axis is parallel to itself. So the angle beta is 0 degree. So we need to find now cos beta. So cos beta equals cos 0 degree, which is 1. Let's consider the angle between the y-axis and the z-axis. The y-axis is perpendicular to the z-axis. So the angle gamma is 90 degrees. So we need to now find the cos gamma, which is cos 90 degrees. Now calculate cos of gamma equals cos 90 degrees equal, which is 0. So putting it all together, the direction cosines of the y-axis are 0, 1, 0. That is cos alpha equals 0, cos beta is 1, and cos gamma equals 0. Now, let's start by finding the direction cosines of the z-axis. First, let's consider the angle between the z-axis and the x-axis. So we call this angle alpha. The z-axis is perpendicular to the x-axis, so the angle between them is 90 degrees. So now let's calculate the cosine of this angle. So cos alpha equals cos 90 degrees, which is 0. Next, let's look at the angle between the z-axis and the y-axis. We call this angle beta. So again, the z-axis is perpendicular to the y-axis, so the angle is also 90 degrees. So cos beta equals cos 90 degrees, which is 0. Finally, let's consider the angle between the z-axis and itself, which we call gamma. Since the z-axis is parallel to itself, then the angle is 0 degree. So let's calculate now cos gamma. Cos gamma equals cos 0 degree, which is 1. Therefore, the direction cosines of the z-axis are 0, 0, 1. Now let's look at the example 5. So in this example, we have to show that the points A 2, 3, -4, B 1, -2, 3, and C 3, 8, -11 are collinear. So first of all, try it yourself and then see solution. So let's solve this example step by step. So the direction ratios of a line segment joining x1, y1, z1 and x2, y2, z2 are x2 minus x1, y2 minus y1 and z2 minus z1. Now let's find the direction ratios for the line segment AB. So we will use the coordinates of A, which are 2, 3, -4, and B, which are 1, -2, 3. So we will calculate each component one by one. So A1 equals x2 minus x1 equals 1 minus 2 equals -1. B1 equals y2 minus y1 equals -2 minus 3 equals -5. C1 equals z2 minus z1 equals 3 minus of -4 equals 3 plus 4 equals 7. So the direction ratios of AB are -1, -5, 7. Now let's find the direction ratios for the line segment BC. So we will use the coordinates of B, which are 1, -2, 3, and C, which are 3, 8, -11. So we will obtain A2 equals x3 minus x2 equals 3 minus 1 equals 2. B2 equals y3 minus y2 equals 8 minus of minus 2 equals 8 plus 2 equals 10. C2 equals z3 minus z2 equals minus 11 minus 3 equals minus 14. So the direction ratios of BC are 2, 10, minus 14. Now check for proportionality. This means A1 divided by A2 equals B1 divided by B2 equals C1 divided by C2 for some constant ratio. Now let's check. A1 divided by A2 equals minus 1 divided by 2 equals minus 1 by 2. And B1 divided by B2 equals minus 5 divided by 10 equals minus 1 by 2. C1 divided by C2 equals 7 divided by minus 14 equals minus 1 by 2. Since A1 divided by A2 equals B1 divided by B2 equals C1 divided by C2 equals minus 1 by 2, some constant, then the direction ratios of AB and BC are proportional. Since the direction ratios of AB and BC are proportional, so we can say that vector AB is parallel to the vector BC. So this is the key condition for collinearity in 3-dimensional geometry. Therefore, we can conclude that points A, B, and C are collinear. Let's look at this question on 3-dimensional geometry. We are given that a line makes angles 90 degrees, 135 degrees, 45 degrees with the x, y, and z axis respectively. Then find each direction cosine. So first of all, try it yourself and then see solution. So let's start the solution of this question step by step. To solve this, let's recall the definition of direction cosines. If a line makes angles alpha, beta, and gamma with the positive x, y, and z axis, then its direction cosines are represented by L, M, and N. These are the cosines of the respective angles. So the formulas are L equals cos alpha, M equals cos beta, and N equals cos gamma. Here L, M, N are the direction cosines along the x, y, and z axis. Now let's write down the values given in the question. Alpha is 90 degrees, beta is 135 degrees, and gamma is 45 degrees. So we will use these values to find each direction cosines step by step. So let's start with L. L equals cos 90 degrees. Since cos 90 degrees is 0, so L equals 0. Now let's find M. M equals cos 135 degrees. We can rewrite 135 degrees as 180 degrees minus 45 degrees. So M equals cos of 180 degrees minus 45 degrees. Since cos of 180 degrees minus theta equals minus cos theta. So cos 135 degrees becomes minus of cos 45 degrees. Now cos 45 degrees is 1 by root 2. So m equals minus 1 divided by square root of 2. This means the line points in the negative y direction with this magnitude. Now let's find n. n equals cos 45 degree. As you know, the value of cos 45 degrees is 1 divided by root 2. So n equals 1 divided by square root of 2. Therefore, the direction cosines of the line are 0, minus 1 divided by square root of 2, 1 divided by square root of 2. Now let's look at question number 2. In this question, we have to find the direction cosines of a line which makes equal angles with the coordinate axis. So first of all, try it yourself and then see solution. Let's start the solution. First, let the line make an angle alpha with the x-axis, beta with the y-axis, and gamma with the z-axis. According to the question, the line makes equal angles with all three axes. That means the angle with the x-axis, the y-axis, and the z-axis are all the same. So we can write that alpha equals beta equals gamma. In other words, alpha equals beta equals gamma. This is a key point because it means the direction cosine for each axis will also be equal. So now let's recall the formulas for the direction cosines of a line. The direction cosine with respect to the y-axis is m equal to cos beta. With respect to x-axis is L equal to cos alpha, and with respect to z-axis is n equal to cos gamma. So we have three direction cosines: L equals cos alpha, m equals cos beta, and n equals cos gamma. Since alpha equals beta equals gamma, so it follows that their cosines must also be equal. So we can write L equals m equals n equals cos alpha. So this is a direct result of the line making equal angles with each axis. So all three direction cosines are equal to the cosine of that common angle. We also know the fundamental identity for direction cosines, that is L square plus m square plus n square equals 1. Now substituting L equals m equals n equals cos alpha into the identity L square plus m square plus n square equals 1, then we will obtain cos alpha square plus cos alpha square plus cos alpha square equals 1. It implies 3 times cos square alpha equals 1. It implies cos square alpha equals 1 divided by 3. Now taking the square root of both sides, we get cos alpha equals plus minus 1 divided by root 3. Now, since alpha cos alpha equals L equal M equal N, so direction quotient of the line are L equals plus minus 1 divided by root 3, M equals plus or minus 1 divided by root 3, and N equals plus or minus 1 divided by root 3. Thus, there are two possible sets of direction cosines for such a line. So, corresponding to the two opposite directions along the line, set 1 for first set of direction cosines is 1 divided by square root of 3, comma 1 divided by square root of 3, comma 1 divided by square root of 3. This means the line makes the same acute angle with each axis and all the direction cosines are positive. The second set is minus 1 divided by square root of 3, comma minus 1 divided by square root of 3, comma minus 1 divided by square root of 3. Here, all the direction cosines are negative, which means the line points in the opposite direction but still makes equal angles with each axis. So, both sets are correct and we have found 12 possible direction cosines for this scenario. Now, let's look at this question about three-dimensional geometry. So, we are given a line with direction ratios of minus 18, 12 and minus 4. Then what are its direction cosines? So, first of all, think about this. How would you approach this question and then see solution? Let's start the solution step by step. To solve this, let's recall the relationship between direction ratios and direction cosines. If a line has direction ratios A, B and C, then its direction cosines L, M and N are calculated using a specific formula. The formula is L equals A divided by square root of A square plus B square plus C square. Here, A is the direction ratio along the x-axis and the denominator is the square root of the sum of the squares of all the three direction ratios. Similarly, the second direction cosine M is B divided by square root of A square plus B square plus C square. In this case, B is the direction ratio along the y-axis. The third direction cosine N is C divided by square root of A square plus B square plus C square. Here, C is the direction ratio along the z-axis. Together, L, M and N represent the cosines of the angles the line makes with the x, y and z axis respectively. Now, let's substitute the given values. The direction ratios provided in the question are minus 18, 12 and minus 4. So, we have A equals minus 18, B equals 12 and C equals minus 4. So, we will use these values into our formulas for L, M and N. So, clearly A is minus 18, B is 12 and C is minus 4. Now, let's calculate the magnitude of the direction ratios. So, the magnitude is found using the formula square root of A square plus B square plus C square, where A, B and C are the direction ratios. So, let's substitute the values into the formula square root of A square plus B square plus C square, which is equal to square root of minus 18 whole square plus 12 square plus minus 4 whole square. Now, calculate each square. We get minus 18 whole square is 324, 12 square is 144 and minus 4 square is 16. So the sum of the inside the square root is 324 plus 144 plus 16. This is equals square root of 484. So this is the total sum of the squares of the direction ratios. Taking the square root of 484, we get 22. So the magnitude of the direction ratios is 22. So we will use this value to find the direction cosines in the next step. First, let's substitute the given values into our formula. Here the direction ratios are A equals minus 18, B equals 12 and C equals minus 4. So we will use these values into the formula of the direction cosines. So let's recall the formulas for direction cosines. The direction cosines L equals A divided by square root of A square plus B square plus A square. M equals B divided by square root of A square plus B square plus A square. And N equals C divided by square root of A square plus B square plus A square. So we obtain L equals minus 18 divided by 22. After simplifying, we will get L equals minus 9 divided by 11. Okay. And M equals 12 by 22. After simplifying, we get M equals 6 divided by 11. And N equals minus 4 divided by 22. After simplifying, we will get N equals minus 2 by 11. Therefore, the direction cosines of the line are minus 9 by 11, 6 by 11, minus 2 by 11. So I hope this question is clear to all of you. Now, let's look at this question. We are given 3 points in 3-dimensional space, which are 2, 3, 4, minus 1, minus 2, 1, 5, 8, 7. And we have to show that the points are collinear. So first of all, think about this. How would you approach this question? And then after that, see the solution. Let's start the solution. To start, let's recall how we can check if 3 points are collinear in 3D. So one way is to use direction ratios. So direction ratios are just the differences in the x, y, z coordinates between 2 points, and they help us describe the direction of a line segment in space. Okay, if the direction ratios between AB and BC are proportional, then the points are collinear. So now let's make this more concrete. So if we have 3 points A, B and C, and we find the direction ratios for vector AB and vector BC, then we can compare them. If the ratios are proportional, it means the vectors point in the same or exactly opposite directions. So the points must be on the same line. So notice that the diagram here, which shows the points and the vectors connecting them. Let's assign the given coordinates to our points. So we will call A equals 2, 3, 4, B equals minus 1, minus 2, 1, and C equals 5, 8, 7. So here we have the points A, B and C and their corresponding coordinates. We know that the direction ratios of a vector from point x1, y1, z1 to x2, y2, z2 are x2 minus x1, y2 minus y1, z2 minus z1. Then direction ratios for the vector from point A to point B, which we will call vector AB. This means we will subtract the coordinates of A from those of B. So let's calculate the x component first. So a1 equals -1 -2 equals -3. So the difference in the x coordinates is -3. Next, the y component b1 equals -2 -3 equals -5. This means the difference in the y coordinates is -5. Finally, the z component c1 equals 1 -4 equals -3. So the difference in the z coordinates is -3. Putting these together, the direction ratios of the vector AB are -3, -5, -3. Now, let's find the direction ratios for the vector from point B to C, that is vector BC. For the x component, A2 equals 5 minus of -1 equals 5, that is 5 plus 1 equals 6. So the difference in the x coordinate is 6. For the y component, B2 equals 8 minus of -2 equals 10. The difference in the y coordinates is 10. For the z component, C2 equals 7 minus 1 equals 6. So the difference in the z coordinates is 6. So the direction ratios of vector BC are 6, 10 and 6. So these numbers show the direction from point B to point C. To check for collinearity, we first look at the direction ratios of the vectors formed by these points. Okay, specifically we need to see if the direction ratios of vector AB are proportional to the direction ratios of vector BC. Okay, this means we are looking for a constant k such that the direction ratios of BC are equal to k times the direction ratios of AB. In other words, each component of BC should be k times the corresponding component of AB. So let's write this out for the x component. A2 equals k times A1. Here, A1 is the x component of AB and A2 is the x component of vector BC. So if this equation holds for some value of k, it's our first check for proportionality. Next, for the y component, B2 equals k times B1. Here, B1 is the y component of AB and B2 is the y component of BC. Again, we need this relationship to hold for the same value of k as before. Finally, for the z component, C2 equals k times C1, where C1 is the z component of AB and C2 is the z component of BC. Now let's check the ratios. So since we have A1, B1, C1 equals -3, -5, -3 and A2, B2, C2 equals 6, 10, 6. So we obtain A2 divided by A1 equals 6 divided by -3 equals -2. B2 divided by B1 equals 10 divided by -5 equals -2. C2 divided by C1 equals 6 divided by -3 equals -2. Since all the direction ratios of vector AB and vector BC are proportional and point B is common to both, so this means the points A, B and C are collinear. In other words, all 3 points lie on the same straight line. This is the key result for proving collinearity in 3-dimensional geometry. Now let's look at question number 5. In this question, we are given vertices of a triangle as 3, 5, minus 4, minus 1, 1, 2, and minus 5, minus 5, minus 2. Okay, and then we have to find the direction cosines of the sides of the triangle whose vertices are 3, 5, minus 4, minus 1, 1, 2, and minus 5, minus 5, minus 2. So first of all, think about this. How would you approach this question? And then see solution. Let's start the solution. To solve this, we first need to outline our approach. So we will break the problem into clear steps so it's easier to follow. So notice that we are focusing on the sides of the triangle, not just the vertices. Step 1 is to find the direction ratios for each side of the triangle. So direction ratios are simply the differences in the x, y, and z coordinates between 2 points. Next, we need to calculate the magnitude of each side vector. So the magnitude is found using the formula magnitude equals square root of a square plus b square plus c square, where a, b, and c are the direction ratios we just found. Finally, to get the direction cosines, we divide each direction ratio by the magnitude of the vector. So if the direction ratios are a, b, c, and the magnitude is r, then the direction cosines are a divided by r, b divided by r, and c divided by r. Now let the vertices of the triangle be a equals 3, 5, minus 4, b equals minus 1, 1, 2, and c equals minus 5, minus 5, minus 2. So now let's take a look at this diagram. It visually represents the triangle in 3-dimensional space, showing the position of points A, B, and C. So for side AB, let A equals x1, y1, z1 equals 3, 5, minus 4, and B equivalent to x2, y2, z2 equals minus 1, 1, 2. Then direction ratios AAB, BAB, CAB are given by x2 minus x1, y2 minus y1, z2 minus z1. So AAB equals minus 1 minus 3 equals minus 4. BAB equals 1 minus 5 equals minus 4. CAB equals 2 minus of minus 4 equals 2 plus 4 equals 6. Now magnitude of AB vector is DAB equals square root of AB square plus BAB square plus CAB square. Now let's expand the squares. So this DAB equals square root of 16 plus 36, and here minus 4 whole square is 16 and 6 square is 36. Adding this together, we have DAB equals square root of 16 plus 36. We can simplify and we get DAB equals square root of 68 as square root of 4 times 17. Okay, this is equal to 2 times square root of 17. We know the direction cosines of a line with direction ratios A, B, C are given by L equals A divided by square root of A square plus B square plus C square. M equals B divided by A square plus B square plus C square, and N equals C divided by A square plus B square plus C square. Here A, B, and C are the direction ratios of the line, and L, M, and N are the direction cosines along the X, Y, and Z axis respectively. Now find direction cosines of side AB. So LAB equals AAB divided by DAB equals minus 4 divided by 2 times square root of 17 equals to minus 2 divided by square root of 17. MAB equals BAB divided by DAB equals minus 4 divided by 2 times square root of 17 equals minus 2 divided by square root of 17. NAB equals CAB divided by DAB, which is equal to 6 divided by 2 times square root of 17, which is equal to 3 divided by square root of 17. Now, for side BC, first of all, let B be at minus 1, 1, 2. Okay, and here we let x2, y2, z2 equals minus 1, 1, 2. And C equivalent to x3, y3, z3, which is equal to minus 5, minus 5, minus 2. Then direction ratios ABC, BBC, and CBC are given by x3 minus x2, y3 minus y2, z3 minus z2. So ABC equals minus 5 minus of minus 1 equals minus 5 plus 1 equals minus 4. BBC equals minus 5 minus 1 equals minus 6. CBC equals minus 2 equals minus 4. Now the magnitude of vector BC is DBC equals square root of ABC square plus BBC square plus CBC square. Substituting the values, we get DBC equals square root of minus 4 square plus minus 6 whole square plus minus 4 whole square. Calculating further, so DBC equals square root of 16 plus 36 plus 16. So DBC equals square root of 68, which is equal to 2 times square root of 17. We know the direction cosines of a line with the direction ratios A, B, C are given by L equals A divided by square root of A square plus B square plus C square. M equals B divided by A square plus B square plus C square. N equals C divided by square root of A square plus B square plus C square. Then the direction cosines of side BC are LBC equal to ABC divided by DBC, which is equal to minus 4 divided by 2 times square root of 17, and after simplifying we will get LBC equals minus 2 divided by square root of 17. MBC equals BBC divided by DBC, which is equal to minus 6 divided by 2 times root 17, and after simplifying we will get minus 3 divided by square root of 17. NBC equals CBC divided by DBC, which is equal to minus 4 divided by 2 times square root of 17, and after simplifying we will get minus 2 divided by square root of 17. For side CA, first let C equivalent to x3, y3, z3 equals minus 5, minus 5, minus 2, and A equivalent to x1, y1, z1, which is equal to 3, 5, minus 4. Then direction ratios ACA, BCA, and CCA are given by x1 minus x3, y1 minus y3, z1 minus z3. ACA equals 3 minus of minus 5, which is equal to 8. BCA equals minus 5 minus of minus 5 equals 10. CCA equals minus 4 minus of minus 2 equals minus 2. Magnitude of vector CA is DCA equals to square root of ACA square plus BCA square plus CCA square. Let's compute those squares. So DCA equals square root of 8 square plus 10 square plus minus 2 whole square. It implies DCA equals square root of 64 plus 100 plus 4. So we can simplify square root of 168 as square root of 4 times 42, which equals 2 times square root of 42. So the magnitude of vector CA is 2 times square root of 42. We know the direction cosines of a line with the direction ratios A, B, C are given by L equals A divided by square root of A square plus B square plus C square. M equals B divided by square root of A square plus B square plus C square. And N equals C divided by square root of A square plus B square plus C square. Then direction cosines of side CA are LCA equals ACA divided by DCA, which is equal to 8 divided by 2 times square root of 42. And after simplifying, we will get 4 divided by square root of 42. MCA equals BCA divided by DCA. This is equal to 10 divided by 2 times square root of 42. And this is equal to 5 divided by square root of 42. NCA equals CCA divided by DCA, which is equal to minus 2 divided by 2 times square root of 42. After simplifying, we get this is equal to minus 1 divided by square root of 42. Therefore, the direction cosines for side AB minus 2 divided by square root of 17, comma minus 2 divided by square root of 17, comma 3 divided by square root of 17. For side BC, minus 2 divided by square root of 17, comma minus 3 divided by square root of 17, comma minus 2 divided by square root of 17. And for side CA, the direction cosines are 4 divided by square root of 42, comma 5 divided by square root of 42, comma minus 1 divided by square root of 42. I hope this question is clear to all of you. That's all for today's lecture, and thank you for your attention. I hope this lesson was helpful to all of you.